Susie.
Quick question. So a lot of the people are asking if we're doing like a live stream.
We are, right now. I just muted the audio, I think.
Okay.
But-
Do you know how they access it? Or
Look up UT Dallas ACM on YouTube.
on YouTube? Okay.
Yeah.
Okay. Thank you.
Yeah. All right, test. Hello, everybody. Can you hear me all right? All right, everybody. Let's quiet down. All right, welcome everybody to the ACM Research Symposium night. I'm glad everyone came. I'll make the intro short because it is late, and the presentations are very exciting, but 10 minutes apiece, so it should take around 40 minutes in total. If you don't already know, ACM Research is a semester-long, student-led computer science research program for undergraduate students. It's one of the divisions within the larger ACM chapter at UT Dallas, and it runs every semester, so you can actually apply to be a part of the program next semester if you think these projects are interesting. So our researchers have been working hard on their projects across this past semester, ranging in topic from cybersecurity, vulnerability analysis, a lot of machine learning, but that's classic in research. And without further ado, I think CC's project is up next, so why don't you guys come on up? Yes.
Okay.
Let's pass out microphone.
Oh, we all get a microphone.
I'll get a microphone. Well, yeah. Mine is dented. Alright.
No. Will that be an issue?
I don't know, what is good lighting? That's too much. Should we do the front?
Hey, y'all?
Oh,
Is that good?
oh,
Yeah.
is this like under, are you using your account?
His
I'm
account.
logged into my account.
Okay, so I think we need to share access to you.
Arian, do you mind giving him editing access? Do you mind giving him editing access for the slideshow?
Yeah. There.
Sorry about this.
Alright. No, you have to give me access to the video itself.
Oh. Is that how this works? I don't know. Oh, there's a lot more people now. You guys got this.
You're still setting up, guys.
Sorry. Okay.
It still shows with the permission.
I think we should begin. Okay.
All right, so hi everyone, and welcome to our presentation on researching interactive game development using machine learning models.
Hey guys, I'm Arne Hassan. I'm a sophomore in computer science.
Hello everyone, I'm Abiola Laladi. I'm a sophomore in computer science.
I'm Kayla Baker, and I'm a sophomore in computer science.
I'm Erin Jacob, I'm a freshman in computer science.
And I'm Naveed McCott, and I'm a sophomore in data science.
For our project, we'd like to give special thanks to our research lead, Cece, as well as our faculty advisor, Dr. Ran Beng.
So our agenda today consists of an introduction to our project, the data set and training, implementation and results, challenges and applications in the real world, and then the conclusion. So our project is about controlling the snake in the snake game using hand gestures instead of a traditional keyboard. We train two deep neural networks to recognize hand gestures and then translate them into game controls that the computer can understand. Our data set consisted of about 1,200 images. We picked 1,200 in order to create variety in our data set with about 300 images pointing in each direction. Then to create our data set, we took pictures of both hands pointing in different directions in multiple backgrounds, angles, and skin tones. We then use our RoboFlow annotation software to annotate and split our data and use the data set to validate, train, and test our machine learning model.
So let's talk about the models that we used to train our data set. We used two models, and we used transfer learning, so we used pre-trained models and then retrained them on the new data set that we created. The first model that we used was SSD MobileNet V2. This is a family of convolutional neural networks, or CNNs, and CNNs are extremely popular for computer vision. Now, MobileNet V2 is commonly used for mobile devices, and this is very important for computer vision because not everything is going to be on a PC. Mobile devices are lower end hardware, so having computer vision running those mobile devices is pretty important. The second one that we used was YOLO V7. YOLO stands for You Only Live Once, and this is the fastest object detection model that we know of right now. It was released earlier this year, July. And it is also the most accurate model on what we call the COCO dataset, which is a very common training dataset that we use for object detection models.
So the split that we use for our data set to train all of the models is that we had 70% of the data set was used for training, 20% was used for validation, and 10% we used for testing. So the first of the three models, the YOLO V7 model, it had a batch size of 16, and it had a step count of 270. The YOLO V7 model had a mean average precision of 99.5, and it had a precision of 98.5, and it had 100% recall. Then the two MobileNet models, the first model we used a batch size of 4 and a step count of 12,500. And then the second model we had a batch size of 16 with a step count of 2,500. And both of the loss for both of the MobileNet models converged around 0.2. And then these two graphs are the MobileNet data. These are loss graphs, so the y-axis is loss, and then the x-axis is going to be the step count. The loss that this is just total loss, and then the white line is the raw data, and then the blue line is more smooth version of that line. And then these are graphs that were generated by YOLO V7. It uses the first three columns are loss, and uses three different kinds of loss. So the first column is the box loss, the second column is the objectness loss, and then the third column is the class loss.
Sorry.
The x-axis on all the graphs on the slide is also a step count, and then the Y for the loss graphs is just loss. For the remaining ones, there's the precision graph, which just has Y axis as precision, and then the recall graph has it, the Y as the recall value. And then the MAP graphs, which is just the mean average precision graphs. The MAP.5 has the intersection over union threshold set to 0.5, and then the MAP.5 0.95 has intersection over union values ranging from 0.5 to 0.95, and it just takes the mean of all of it.
So let's talk about some challenges that we faced when doing our projects and some changes that we make in the future. The first challenge was the data set was not varied enough. The hands that were in the data set that we used were all our hands. It was just us five creating those. And it was also taken with uniform background and very similar lighting conditions because it was all shot on one day. So this meant that the model was better suited for certain skin tones under certain lighting conditions, normally bright conditions. This meant that when the model went outside those data sets, so when the live stream showed a picture that was not exactly fitting the data set, we got a different classification or an error or no classification at all. And another challenge we faced was with labeling data set. We used Label Studio originally, and we ran into issues with free trials because it is a paid service, and importing and exporting data to and from the project was also a hassle, so we ended up using Overflow. Lastly, we would like to make one change, and that would be voice recognition. So instead of pointing up, left, down, or right with our thumb, we would say up, left, down, or right, and have the computer control the stick that way.
All right, so speaking of challenge number 3, incorrectly classifying hand gestures, here's an example of that. You'll see that I'm trying to show a right hand gesture. It looks left, but from my point of view, it's a right hand gesture. You'll see that it's being incorrectly classified as an up hand gesture. And very funnily enough, you'll see that the chair in the background is also classified as an up hand gesture. Pretty unexpected. But the problems with this might have been because of overfitting. And overfitting is basically when the model is memorizing the training data that we give it. So it's not able to generalize on that data. Next slide. You'll see here we have 2 more images. The second image, or the first image on the slide, you'll see that the model is able to correctly classify this hand gesture as a down hand gesture. But you'll see on the image to the right, no classifications are drawn onto the image because the model wasn't confident enough to make that prediction.
So, with connection to our machine learning model, our applications in the real world would involve things like computer vision. Computer vision is a technology where we try to imitate our human interpretation of the world around us, but within computers, at least on a surface level. And you can see this technology within like Teslas with their self-driving, or facial recognition with your phones, and even like the towards industry with their object detection. Moving along, if you look at the interactive entertainment industry, things like the Xbox Connect a while ago, they use like AR, augmented reality. Although that isn't exactly like what we're looking for here, it still involves computer vision concepts such as object detection. And as we progressed through the years, the entertainment industry got more into mixed reality and virtual reality. And as we go along, things like our model will be able to help progress this industry and make the games, or make this platform more appealing. And finally, our main focus was to target those with disabilities, such as Parkinson's or cerebral palsy. For those who can't use the traditional controller, they'll be able to use their hands instead of the normal controller to be able to control these games, at least to the extent that we would be able to. In conclusion, it is it is plausible that we have to implement transfer learning to pre-train object detection models to detect directional hand gestures. I wanted to get the terminology right. And it is imperative that we, moving forward, that we increase the variety within our data set to reduce any unwanted biases in the future.
Okay, let's All right.
All right. Okay.
So here's a demo of our game. The goal essentially is for the snake to grow by collecting food, which is red on the screen, without hitting walls. And you can see I'm trying to control the game using hand gestures, but I used the up hand gesture kind of too early, so I hit the wall and didn't get the food.
All right, thank you all for coming. If you have any questions, feel free to ask us. I'm all here for us. All right. Oh yeah, that's someone actually.
Did you think about like using similar controls for other types of games? Like, how did you decide on Snake?
We decided on Snake because it's a pretty simple game to create, and it's up, down, left, or right. There's no like turning or anything like that. That would take too long.
Yeah, I was just thinking it would be cool to play like Mario Kart or something and like steer like this, but I guess that's not just like forward direction.
Alright.
Do you ever think of using like multiple fingers or at least a different finger for the thumbs? Because the thumb, there are a lot of like possible positions you could put your hand in, like the thumb point in one direction as opposed to say you have your entire hand, like four fingers pointing in that direction. There are a lot of gestures possible.
Yeah, I think with that, I think the thumb was just like easier to like move very quickly. Like if I were using the whole hand, it'd be a little bit harder to like point it down from pointing up. Unless people did this, and I don't really know if that would be possible for someone who would have like a new disability. Like, especially if you have carpal tunnel, which is very common now, people would have trouble moving their wrist as quickly.
Well, if some changes that we can make to our project basically is we can add more of those hand positions so that we can better cater to people with different types of hand disabilities, so that the model can be able to detect like different fingers, multiple hand gestures, not just one hand gesture, with the game that we're developing, basically.
All
Alright, that's, we'll have one more question.
Okay. Hey, go ahead.
So how did you guys get to number 1200? Is it just a random number, or if you did increase the sample size, by how much would the accuracy increase?
I'm not gonna lie, we just did like first shots of moving the camera around, and we just like timed it out like 5 seconds, and we just got like this huge number, and we're like, this should be good enough.
I think that the original goal was like 500, and we ended up just taking more. We did the first thing and ended up with 500.
I will say that if we were to add more images, it would be more varied environments and not just like first shots of ducks. Alright, that should be it, right?
Yep.
Alright, thank you.
Thank you.
Turn it off first, yeah.
All right. All right, have you guys shared the slideshow with me? Perfect. Perfect, thank you so much. Yeah, did you guys rely on speaker notes? Like in Google Slides?
No, I don't have any speaker notes.
Awesome, okay. I will start the slideshow.
I want a microphone too. I want to throw the microphone.
All right. Let's see. Yeah, okay.
Camera, and that's the
All right. We're getting ready for our second presentation here. Thank you very much. So, does anyone here distrust the programs that they use? Yes, there we go. Besides privacy concerns, many of the apps we use might be insecure, and data breaches happen all the time. So I'm glad that there's research teams like this to try to solve that for us. Can you please welcome Pranav's team over here? Here, go ahead.
Thank you. Man, what a great team, huh? I want to get your microphones. Get mic'd up. Hey, can we switch the slides over?
Okay.
Oh, there's more microphones. You can use those.
Yes, you can use microphones. All right. Great technology.
This one has a divot. Hello.
You got Are they all on?
You have to turn them on.
There's like a.
Hello.
Yeah.
Is that loud enough?
Yeah. Yes, our technical difficulties. It's just we're security vulnerabilities for stuck in the basement. We don't use microphones. So we got our presentation. You don't want to talk to a bunch of strangers, do you? There's strangers everywhere, stranger danger, okay? And so let's go ahead and introduce yourselves. I'm going to introduce myself first. My name is Austin Lang, let's see this person. I'm Rashid Birrell.
I'm Adit Tazapur.
I'm Hajj Developer.
I'm Chris. And so that's our team that we're going to have today. And so what we're going to talk about today, let's talk about our slides. It's like everyone's dream. And we're going to talk about every nerd's dream we have today, okay? And that's going to be hackers. Can you see the slide, please? Oh my gosh, hackers. Remember talking about researching hackers. No, that's easy, okay? You can smell them from a mile away. It's like, hundred smell. And then you also tell by Twitter.com, right? They're bragging on Twitter.com, they're posting every minute, okay? No, we're not talking about researching hackers. We're going even higher. We want to become hackers, but that doesn't mean we're going to jailbreak our iPhone. That doesn't mean we're going to run Doom on our smart fridges. No, we're going even higher than that, all right? We're going to become security vulnerability researchers. And so let me today our project for finding security vulnerabilities in open source projects. Okay, so what does this mean in general? Well, we didn't become hackers, okay? I know it's such a disappointment, but by the time you get in university, you're already, used to disappointments in life. Well, so what does that mean really? Let's go ahead and take it to the next slide. What is a security vulnerability? I want to take it to our pro IT person, Chris Back, and tell us what it is.
Please. Thank you. Yes,
It's not on.
Yes, I am the only senior amongst a team of freshmen and only IT student. But we play games. Security vulnerabilities is basically like speedrunning a game. And so rules are just going to be things that you can get past. And then vulnerabilities are actually features that you help to get speedrun through your game. And so on a more serious note, vulnerabilities are what hackers use to exploit vulnerabilities to cause some type of threat to an organization. Say something like granting unauthorized access to a system or a network. And so if we could go to the next slide, we have a demonstration.
What do you want, Chris?
$20 for drugs.
What of Chris want?
Script open tag, quote bracket open tag, $20 course bracket tag plus script tag.
Of course, Chris, here's your 20.
Thanks. That was a very mediocre attempt at cross-site scripting. So if we go to the next slide, cross-site scripting is an example of a vulnerability. And so what this does is a malicious actor can pass some sort of specific characters to something like a URL form, and basically takes advantage of the URL raw data to execute some type of query or front-end JavaScript. So to grant unauthorized access. So yeah, that's one example, but for the next slide, we have tons of other common vulnerabilities, and so you can go through that. There's SQL injection, and that. So most importantly though, we want to be able to mitigate these, and so how do we fix this in a world full of vulnerabilities? And the next slide, it's through awareness and debugging. So now our Linux professional leadership will help us.
All right, sweet. So let's talk about awareness here. Okay, so right here we see the CVE website, which is essentially a list of documented vulnerabilities. This is also funded by the United States, and what I'm trying to say here is, what's the purpose of this, right?
So when programmers write their code, it's really important that they take care of security measures. So this helps them like check through any security measures that might be in their code, and it also helps them explain to their users that our systems might be affected here. Let's go to our next slide. Okay, so let's get to my favorite topic, Linux. So in Linux, everything runs off these ELF binaries, so ELFs. This stands for executable and linkable format files, which is essentially like your .exe on Windows. So like you can run your browsers or your games and everything, but this is Linux specific. So there's an ELF there. But when a programmer creates an ELF file, they have the opportunity to use they have the opportunity to essentially put in special information about their program in the binary. This is called the debug frame. Now, a great way to represent this debug frame is using dwarf data. Now, dwarf does not mean there is a tiny man running around in your code, but it does mean that you can debug your code pretty efficiently. It also means that you can use this dwarf data to find security vulnerabilities, which we'll talk about later. Remember this duo because it will come in handy later on when we talk about these things. But that's about it for the basics.
Our project starts with our method. We work with both Dr. Kevin Hamlin and Dr. Shimilo Okromasuria to narrow down the programs we would check for security vulnerabilities and the tools we would use to do so. With their consent, we were able to gain access to his and Eric Bowman's security vulnerability scanner, known as EarlKing. Now, how EarlKing works is a little bit complicated, so I'll try to make it simple. EarlKing is based on Journ, a source code analyzer, and uses both the source code and resulting binary ELF file in order to find vulnerabilities. Basically, it takes the very foundations of a program, the code, and the resulting program from that code, and creates a graph out of it. This graph is called a code property graph, CPG for short. This graph uses the little dwarf debug data we mentioned earlier and the resulting code, and that is then formatted for code querying. Now that last step is important because EarlKing's main way of finding vulnerabilities is through the code query of the graph and consequently the memory layout of the program as well. So basically, with the physical analogy, we're trying to map out the program's brain and see how its neurons think and move information around. So EarlKing became the main crux of this project, our ticket to easily finding a vulnerability, except it's never that easy. Security vulnerability scanners only indicate what could possibly be a vulnerability. The number of false positives is relative to the size of the program and the scanner itself. EarlKing's method of querying CPGs results in a reduced number of false positives compared to other scanners. However, that number still isn't zero. So we took this into account and began our search for finding vulnerabilities. So let's go ahead and transition to actually using EarlKing.
So there we were in the open source jungle we call GitHub and all the other hubs I will explain. But let's say I was there and I was looking for it, alright? And so I was walking there and what I found was the open source Debian library. Hit it with them. And hit it with them. Oh my gosh, it's so beautiful. I cry every time. I can't tear up anymore. I'm tired. Anyway, so this has everything we needed. All the requirements we needed for EarlKing to work, okay? So EarlKing needs Linux C compiled programs, right? And these C compiled programs need to be ELF files and they need to have dwarf data, okay? And those are important. So we tested all these programs from the Debian library. Our very, very friendly Debian. And so we went through all of them and we tried to look through all the programs. So the large programs weren't working, and so we were saying, okay, let's go ahead and keep moving on to only we're running out of time, and so we're saying, okay, let's all look at small programs, okay? Because one main thing that EarlKing has a problem is called time complexity. And what time complexity is basically we're spending too much time doing this large program. We have a computer scanning, we have EarlKing scanning this big program called PhotoQT or FFmpeg, and it's taking forever, all right? It's taking weeks. I think one of our computers is still scanning it right now. And so we're going to go and narrow it down to two small programs, Volt and CPU Limit. And so I'll have our resident computer expert, Adam, to go ahead and tell us about it.
So Volt is a Linux daemon that connects and interfaces directly with Linux Thunderbolt hardware. And CPU limit specifically, as its name suggests, simply limits the amount of CPU the program can use. Basically, what we did, we took these two individual programs, threw them into EarlKing, and this is what resulted. So EarlKing essentially checks for a few different types of events in our code, right? It checks for different types of affected variables, user-affected variables. It checks for insecure calls, buffer overflows, and irreducible for loops. Out of all of, so we noticed, so when it spat out was, so we got 628 different pointer null checks, which, I mean, reminds me how much work I did, right? A lot of work looking through all this source code. Anyways, it turns out all those 620 were pretty innocuous. There's really nothing we could do about them. What remained was this one insecure call, or a couple of insecure calls in Volt that related to the handling of user IDs. As it turns out, there were other measures put in place so, you know, our ascendance to the world of elite hackers never came to fruition.
So, thank you so much, buddy, for your hard work. So what does that mean? Well, that means, sadly, we were disappointed also, and we didn't find a security bug, so boo-hoo. But I think we can accomplish our goal in other ways. You know, when we started out, we didn't know very much about this project. We're all freshmen coming in, and I guess it's IT senior there, you know. But like, we came in this without knowing anything, and so I think us as a team really stood up and took it together to find out everything about this. And so I would like to thank ACM for having us here, and our ACM director, Roman, here. What a wonderful guy. And also our wonderful project lead, Parag Nair. Thank you very much. And so that pretty much puts it out there. That's been me, Lawson Lane.
Chris.
Kanchan.
Adit.
Christian.
And that has been our slides. If there are any questions, we can do it in like 1 minute. All right, thank you. Questions? Anyone got questions? Yes, you in the back. So we did talk about fuzzing with the professor, Dr. Shima. He said he wanted to go with guided fuzzing after using EarlKing, and so that is a possibility that we're thinking of. Yes. Anyone else? Really? No one? Okay, wow, you know what? You guys are experts already. You know, good on you. All right, thank you, thank you. Good job, everybody. Thank you so much.
I think it's our team going next. There's me next. Come on, Roman.
Yep, you guys are going. All right.
And for the demo, how do I turn these lights on?
Yeah, I would actually turn the screen.
Yes. I like, no, for the demo, like, we need like kind of like all slides off. So just for like the 30 seconds, I'll close all lights off if that's okay.
Yeah, sure.
Okay, cool. That works.
And do you need a laptop for your demo?
No, it's like all contained in the slideshow, so it's okay.
Awesome. And then turn off.
Yes.
Turn off this. Not right now, but to turn off all the lights.
All right. Just the front one, right?
Yeah, just front.
All right.
All right. Can I get a mic?
Mic. All right, guys. You guys got it.
All right.
You got way too quiet.
All right. Can I get one show of hands? Can you tell me your favorite animal?
That's the man right there!
Hey, this guy knows what's up. All right. I think this team needs no introduction. Take it away.
We are Yolo Academy. My name is Aryan Punjabi.
I'm Cesar Yanis.
I'm Marvin Sarkar.
I'm Aditya Desai.
And our research lead was Abhishek Mishra. Before we begin our presentation, I want to give a big thanks to Dr. Karen Mazzini who's our faculty advisor. She has many achievements under her belt, including being the nominee for Best Paper in 2016 from the Intelligent Tutoring Systems Conference, being a Grace Hopper Scholar in 2015, and winning first place in the UNT Graduate Exhibition in 2014. Again, a big thanks to Dr. Karen Mazzitti for her help on our research project. One half of traffic fatalities occur at night, which is surprising considering only 1/4 of travel occurs at night. This phenomenon can be attributed to many factors, including drunk driving and fatigue, but most importantly and prominently, impaired vision during the night. Taking this into consideration, our team sought out a big technology that helps to see in the night, and we already found we use thermal cameras. Essentially, thermal cameras take in heat that's produced by objects in the environment and maps out like a map of the environment. It works really well during the night compared to RGB cameras, which get affected by glare. So think about all of this, our team came up with a research question: can we train an AI model such that it effectively detects objects in thermal images?
Right, so with the research question in place, we can now get into the context of how we actually went about developing the solution, starting with the actual data collection. So the data set we used was Teledyne FLIR's directory of thermal images. Now, Teledyne FLIR is a company that specializes in providing providing thermal imaging cameras for both consumers and businesses as well. However, they have a public directory with over 26,000 images taken from these thermal cameras. And on top of this, they're formatted specifically for supervised object detection, having training, testing, and validation files, each annotated with over 15 classes, such as people, bikes, and cars, and even ranging down to skateboards, strollers, and scooters, things that an ADAS system would need to detect. As for the model, we went for YOLO. YOLO stands for You Only Live Once, and as you can see here, YOLO has many different iterations. It is currently the benchmark in open source object detection. The iteration we use is their newest YOLO V7, which, as you can see here, has a batch 1 inference time far less than any other YOLO iteration that's come before it, and has far better accuracy. However, YOLO V7 was trained using RGB images. We're using thermal imaging. So they're two different fields which have similar points to them. So what we did, rather than simply starting with the data set from scratch and training that, we used a process known as inductive transfer learning. So with inductive transfer learning, we took the knowledge base already developed by YOLO V7, and then we merged that with the Teledyne FLIR data set. By doing this, once again, we were able to keep the efficiency of YOLO V7 while extracting the key and distinct features from the Teledyne FLIR data set. And here's just another diagram of the transfer learning process which we used. As you can see in that top left node, we have the YOLO V7 source data, which when the proper weights are applied becomes YOLO V7, the model itself. And through this inductive transfer learning process, we were able to merge the Teledyne FLIR data set to get YOLO V CAPI, which ended up performing our end product, which was object detection with thermal imaging.
So let's move on to our demo. Right here we have on the left the RGB image, that's supposed to be the RGB image, that basically is running on the base YOLO V7 base. As you can see, it's pretty hard to detect any of the objects that are blocked by the really low light, not low light, but problematic lighting conditions here. So that's a problem, right? So for that, we came up with a solution of using thermal images and training the YOLO V7 to basically detect objects for that thermal image. So if you just take notice, there's a kid running across the image, and because of the light conditions, it was a bit harder for the base YOLO V7 base to detect it. So yeah, that's pretty, that's it, honestly. So let's move on to the results for our model. Before we do that though, actually, I would like to mention that our data set is 10,000 images, but it's really imbalanced. So some classes have way more labels than others, and so that shows in our results here. If you look to the top right, the accuracy for person label or class detection was way higher, 83%, than any of the other ones. Not actually, cars were higher than that, but it's basically because of the fact that persons and cars have way more label information than any of the other ones. The false negatives, again, pretty bad. I would like to take like you to take notice of the skateboard and scooters and other vehicles. They were extremely bad because of the low amount of labels. So let's move on to the F1 scores. Again, you can see the imbalance with like the data set, the person, the orange line performing, having way better F1 scores. I should actually mention that F1 scores are basically the harmonic mean between precision, of precision and recall. And so that's basically just a representation of precision recall. So the higher it is, the better the precision the recall. So let's move on to the mean average scores. Our overall score was around 50%. Not great, but that was only because of the fact that our the skateboard, scooters, and other vehicles brought it down quite a bit. The two main focus, the classes we focused on, the two main ones, the persons in car, because they had the better label information, had around 90% accuracy, precision, sorry, mean average precision.
Okay, here again, you can see how well our model actually performs, even in a situation where, as you can see here, there's a bunch of cars or in general objects overlapping in the back, and it still pretty successfully identifies each individual car in the back here. So basically, the FLIR dataset was previously only tested and run on the YOLO V5. That is basically the YOLO X. In this graph here, you can see first the YOLO X run on RGB images, on thermal images, and then our YOLO VCAPI model run on thermal images. The difference between those here, specifically, you can see how well thermal imaging in general performs compared to our RGB images, and then how our model basically, well, yeah, shows better results than the YOLO X on thermal imaging. Why is that specifically? Like I said, the YOLO X model was run on YOLO V5, so the previous model before YOLO V7 came out. So YOLO V7 has so far not yet been, until we basically did it, been trained and run on thermal imaging. And by showing that our model is outperforming the previous model, we're basically setting a new benchmark for specifically the FLIR data set and thermal imaging.
Now, given the relative success of our model, it can be hypothesized that thermal imaging serves as a valid solution to object detection in poor lighting conditions. This is especially beneficial in the automotive industry, where this application could reduce the reaction times of drivers by providing alerts, but can also help autonomous vehicles better guide themselves through pathways through the better understanding of the scenario, the situation, and things you're looking at. Now, given the relevance, what can we do to improve this in the future and in future works? The first thing we want to look at is the diversity of data. Our training model was very much limited to the FLIR dataset, and while that was very extensive in the amount of pictures and frames it gave us, it had some limitations. The first thing is, we want to look at a dataset that has more edge cases than what the FLIR dataset had. We also want to look at data that gives us an ability to classify more objects like animals and other objects like that. Another thing we want to add on to our model is additional features. One feature we'll look at is the ability for our model to detect the distance between objects and the trajectory of such objects in order to prevent incidents and better prepare for oncoming collisions. Now, as for our references for our presentation itself, these are our references. And thank you for your time, and do you have any questions?
I think it's all of them actually, because when I was doing detecting, basically all running through the test images, it was going through all those. It was misidentifying a lot of false negatives, a lot of smaller signs and lights and stuff. That was one of the bigger problems. I think it's probably both basically imbalance in how many labels there are, and then just the size of the object itself. And if he uses image size of 640 by 512, I think, so if it was a bigger size, if he had just run it through a bigger size, like during the model training, might have been better, but computationally it takes way longer, so yeah.
Do you plan to switch from a single stage detector like YOLO to a two-stage detector like faster ACM or something like that?
We did not look at that just yet. So, yeah, maybe we would do that. I don't know yet.
All right, thank you.
Thank you.
Come on up.
Let's go, Chris!
All right, awesome. That's great. I feel like that project could be especially useful as the future goes on and self-driving cars become more common. Now, most people think that artificial intelligence systems are black boxes that we can't really peer into, but explainable AI is I don't want to say relatively new, but it's becoming more popular. It's a field that looks into behind the scenes how AI systems work. And with that in mind, I'd like to introduce Logan's project about applications in explainable AI in medicine. Thank you very much.
So I'm Rohan.
I'm Sixer.
I'm Joe.
I'm Ben.
And I'm Chris.
And our project is called Applications of Explainable AI in Medicine. So what does this actually mean? Well, explainable artificial intelligence, or XAI, is a solution to a commonly seen problem in machine learning. As AI algorithms become increasingly complex, humans have a more difficult time comprehending what's going on behind them. This creates a black box under the hood, in which people cannot understand what's going from input to output. Even the data scientists and engineers who create the models can't explain what's actually going on within them. On the other hand, XAI allows us to take a closer look into these models and understand what's happening. We can determine biases and characterize a model based on transparency, fairness, alongside many other factors. Due to all these benefits, we're starting to see much more use of XAI in a variety of fields. Well, what are these fields? Well, the use case of XAI is actually limitless, but just to name a few, we're starting to see some use in the automotive industry for things like autonomous vehicles. When a vehicle makes safety-critical decisions like taking a turn or following a path, without these things being explainable, the pedestrians and passengers near these vehicles are put at risk. That's why XAI can help make these decision-making processes more trustworthy. In the military, there's more discussions of using XAI for things like autonomous turrets. If a turret can lock onto something and shoot it automatically, we must understand why and how it's doing this, or else there's a lack of trust, a lack of transparency, and danger involved. Lastly, the field that we're actually trying to implement XAI into is medicine. Machine learning algorithms used to diagnose certain medical conditions are starting to become a reality. However, certain biases and flaws in the decision-making process or data sets used to make these models are all behind the black box. Especially in medicine, these factors are super important because a patient's trust has to be retained in medicine. Furthermore, improper judgment when diagnosing someone with a medical condition leads to significant harm. Thus, we are trying to implement XAI for medical data sets for specific conditions in order to expand the uses of explainable artificial intelligence.
The main XAI technique that we are using is folder RM. Folder RM is an algorithm that's written in Python and will generate a set of rules based on a inputted tabular data, like spreadsheet, for example. These rules can then be viewed and analyzed by humans in order to notice patterns, correlations, and biases in the data. And folder RM also comes with a justification module that can be turned on in order to further explain how it is creating these rules for the data set. These rules can even be used to make new predictions for new data. Because the output of folder RM is actually in Prolog, which is a programming language that generates predictions based off a set of provided rules.
All right, the medical data set we used was a diabetes data set conducted by the CDC, and it was a behavioral risk factor study. And this was available on Kaggle. Our data set was comprised of roughly 250,000 individuals. It had 21 total feature variables, namely high blood pressure, high cholesterol, did we eat vegetables, did we eat fruits, and did we have access to healthcare, etc. This was distributed roughly to 4,500 people having prediabetes, 35,000 having diabetes, and the remainder having prediabetes. Why is the FoldRM algorithm useful on this data set is because we can now explain what we find. And diabetes is very, very common and often undiagnosed. For example, roughly 88 million adults in the US, approximately 1/3 people have diabetes, and 84% of them do not know it. Furthermore, 31 million in the US were diagnosed with diabetes, and roughly half of them did not know they had it. Utilizing the FoldRM algorithm on this data set allows us to identify key feature variables that are primary indicators for diabetes. Our goals were to analyze the Prolog rules produced by our algorithm and explore XAI possibilities and examine the extent of the algorithm. And now on to our
Okay, this is our like demo websites. It can be used by the doctor or like some people who want to test their diabetes. And when they input like 21 numbers, such as like age or the income level or the higher BP, like this, and back to the website, the website will tell them he have like pre-diabetes or diabetes or no diabetes detected. To analyze this, there's 3 cases for the no diabetes, and up right 3 cases. For the first cases, the higher BP had to be negative or like 0, but they have like value for 1. For the second cases, the higher BP is value 1, and we have to look at 4 more conditions. In the AB3, AB9, AB11, AB16 have the common conditions, and the high call value was 0 for him. So second cases is agreed to tell them to there's no diabetes detected.
So with our results, we found that our model on the large datasets generally had an accuracy around 85%, and on a smaller subset that specifically tested for acute symptoms, it had an accuracy of around 73%. These are bad numbers, but this is not what we would like to see out of a like cutting edge model to detect diabetes. There's much more effective diabetes models available. But the advantage of this, of course, is that it's explainable, which leads us to a compromise between the two models called mixed use. So the trainer, the scientist who's training the model can use the explainable AI to tune the data set. So essentially, before training it on a conventional statistical learning method like a neural network, which is typically more accurate, we would train it with explainable AI. And we would analyze the rule to see if there are social biases present or anything else that would reduce the accuracy of the model. For instance, in our model, one of the things we found is that there is a very small correlation between access to healthcare and having prediabetes. And what we can reasonably look into that and see is that people who have access to healthcare are more likely to go to a clinic and get diagnosed with prediabetes, not that they're substantially more likely to have diabetes. And what we can see is using that explainable AI model can tell us where some of those biases exist. So when we use it in conjunction with a statistical method, we can have a much more effective and much more socially productive result at the end of the day. And that's our presentation. Thank you.
So when y'all got the data set, did y'all pre-process it or like find out the Shapley values of each of the features?
So there's some moderate pre-processing. The data set, we mostly use it as is because we wanted to detect stuff after the fact. I don't know the Shapley values offhand.
Oh, okay. Because I thought, my question was going to be like, would you know like what feature impacted your rules the most? Right?
I think, could we flip back to J1's? So, that one, yeah. So this is the set of rules, I believe, for the acute data set. And I think one of the things we can see here, just from the first two, which are typically the most important rules, is that like the high blood pressure, especially, was the most influential in diagnosis, which makes sense given what we're diagnosing.
Thank you.
We have time for one more question.
So the idea behind mixed use is that you use these like explainable rules to remove biased data points from the data set and then use regular machine learning on that transformed data set. Is that right?
Yeah, so the idea behind mixed use is that you can reduce, like you can help it to like help pre-process the data set essentially. Ideally you use the explainable AI directly on the data set, but given current limitations around its accuracy, mixed use is the best compromise to get some of that accountability and reducing bias while also maintaining accuracy.
Okay, it just seems like that would still give you just a black box that is something magic.
So it's, yeah, at the end of the day, there is still some black box, but we have an idea of reducing bias. It's not, but the compromise behind mixed use is that you only reduce part of it. So there is still a black box there, but we do reduce some of the black box, so we get some idea of what's going on.
All right, thank you so much.
That concludes the presentations of the 4 research projects for the ACM Research Symposium. And over on the right, I believe, are the 4 posters. And shortly, each of the teams will be standing around their posters to answer any further questions you might have about their projects. Thank you so much for coming to the ACM Research Symposium.